Everything you think you know about how the world works is completely wrong. You probably think that if you leave your car in the garage, it stays there until you come back. Or that if you look at a tree, the tree doesn't care if you're watching it or not. In our everyday lives, things are solid, predictable, and they follow simple rules. But if you shrink down past the atoms, past the nuclei, and into the basement of reality, common sense doesn't just break, it gets hit by a freight train. Down there, in the quantum world, objects can be in two places at once. They can communicate across the galaxy instantly, and they literally don't exist in a set state until someone looks at them. It sounds like a ghost story, doesn't it? Well, even Albert Einstein thought so. He spent his life trying to prove that this spooky action wasn't real because he couldn't accept a universe that was so fundamentally weird. But here is the kicker. Einstein was wrong. In this video, we are going to peel back the curtain on the most mysterious force in existence, quantum entanglement. We're going to see how two particles can become twins that share a single soul, no matter how many millions of miles separate them. We'll look at the famous fights between the greatest scientists in history and see how they tried to make sense of a world that refused to make sense. We are also going to explore how these quantum ghosts are being used today to build computers that can outthink the entire human race, and how they might even be the glue that holds the fabric of space and time together. If you've ever felt like there is more to the universe than meets the eye, you were right. By the end of this, you'll never look at a piece of dust or a distant star the same way again. This isn't just science, it's the secret operating system of the cosmos. To understand the ghosts, we first have to understand why they are so scary to scientists. For hundreds of years, we followed the rules of a guy named Isaac Newton. His version of physics is what we call classical physics. It's very comforting. If you kick a ball, you can calculate exactly where it will land. If you know the position and the speed of everything in the universe, you can basically predict the future. It's like a giant clockwork machine. But then, in the early 1900s, we started looking at the tiny stuff, like electrons and photons, and we realized the clock was broken. The first big shock was something called wave-particle duality. Imagine you have a wall with two slits in it. If you throw tennis balls at it, they either go through the left slit or the right slit and hit the back wall in two piles. Simple, right? But if you fire tiny particles like electrons at those slits, they don't act like tennis balls. They act like ripples in a pond. They interfere with each other and create a pattern of many stripes on the back wall. This means the electron isn't just a little ball of matter, it's a wave of maybe. It's spread out across space. But here is where it gets truly creepy. The observer effect. If you put a camera by the slits to see which hole the electron actually goes through, the electron notices. It stops acting like a wave and starts acting like a solid ball again. It's as if the particle knows it's being watched and decides to behave. This suggests that the very act of looking at the world changes the world. In the quantum realm, there is no such thing as an objective reality that exists without us. This leads us to a concept called superposition. This is the idea that a particle doesn't have a set location or state until it's measured. Before you look at it, it is essentially in every possible state at the same time. Think of a spinning coin. While it's spinning on the table, is it heads or tails? It's actually a bit of both, a blur of both possibilities. Only when you slap your hand down on it does it choose a side. Now, imagine a cat in a box with a bit of radioactive material that might or might not kill it. This is the famous Schrödinger's cat thought experiment. According to quantum mechanics, until you open that box, the cat is both alive and dead at the same time. It sounds like nonsense, but in the math of the universe, it's the absolute truth. As you can imagine, this maybe version of reality didn't sit well with everyone. The biggest hater of this idea was Albert Einstein. He was a man of logic and order. He famously said, "God does not play dice with the universe." To Einstein, the idea that things only became real when we looked at them was ridiculous. He believed in local realism. This is the idea that objects have definite properties even when we aren't looking, and that things can only be influenced by their immediate surroundings. In 1927, the world's smartest people gathered at the Solvay conference in Belgium. It was like the Avengers of science. On one side, you had Einstein. On the other, you had Niels Bohr, the leader of the Copenhagen interpretation. Bohr argued that we have to accept the weirdness. He told Einstein, "Stop telling God what to do with his dice." This wasn't just a polite disagreement. It was a battle for the soul of science. Einstein would spend his breakfast time coming up with riddles to prove Bohr wrong, and Bohr would spend his day figuring out the answers. The climax of this fight happened in 1935. Einstein, along with two other scientists named Podolsky and Rosen, wrote a paper that introduced what we now call the EPR paradox. They thought they had finally found the gotcha moment. They pointed out that if quantum mechanics were true, you could have two particles that are linked in such a way that if you measure one, the other one instantly changes, no matter how far away it is. Einstein called this spooky action at a distance. He argued that since nothing can travel faster than the speed of light, this instant connection was impossible. He concluded that quantum mechanics must be incomplete. He thought there must be some hidden variables, some secret instructions inside the particles that we just hadn't discovered yet. He died, believing that one day we'd find a more sensible explanation. So, what exactly is this spooky action that Einstein hated so much? It's called quantum entanglement. To create an entangled pair, you usually take a single particle and split it into two, or you make them interact in a very specific way. Once they are entangled, these two particles are no longer separate individuals. They are part of the same wave function. They are essentially the same thing, just in two different places. Think of it like a pair of magic dice. If you take one die to New York and the other to the moon and roll them at the exact same time, they will always match. If the New York die shows a 6, the moon die will show a 6, every single time. Now, in the normal world, you'd assume the dice were rigged or that there was a radio signal between them. But in the quantum world, there is no signal. The connection is instant. It happens faster than light. It happens at exactly the same moment. This is often explained using a property called spin. In quantum physics, particles have a spin, which is like a tiny magnetic direction. They can be spin up or spin down. Because of certain laws of the universe, like the conservation of angular momentum, if you have two entangled particles, their spins must be opposites. If one is up, the other must be down. The weird part is that neither particle has a set spin until you measure one. Before the measurement, they are both in a superposition of up and down. But the second you check the first particle and see it's up, its twin, which could be on the other side of the galaxy, instantly becomes down. Now you might be thinking, wait, didn't Einstein say nothing can travel faster than light? And you're right. This is where it gets tricky. While the connection is instant, you can't actually use it to send a text message or a piece of data faster than light. Why? Because the result of the measurement is totally random. You can't force your particle to be up to send a signal. You just observe what it is. Because you can't control the outcome, you can't send information. So, Einstein's speed limit for the universe stays intact, but the spookiness remains. This is what we call non-locality. It's the idea that distance is basically an illusion. On a fundamental level, everything in the universe might be connected in a way that ignores space and time. For decades, the Einstein-Bohr debate was just philosophy. There was no way to actually test if Einstein's hidden variables existed or if Bohr's spooky action was real. That changed in 1964 with a man named John Bell. He was a physicist from Northern Ireland who worked at CERN. He came up with a mathematical formula called Bell's inequality. It was a genius way to settle the argument once and for all. He proved that if Einstein was right and there were hidden variables, then there was a limit to how often those magic dice would match. If Bohr was right and the particles were truly connected by spooky action, they would match more often than that limit. The math was there, but the technology wasn't. It took until the 1980s for a French scientist named Alain Aspect to perform the first really solid experiment. He used lasers to switch the settings on his measuring devices so fast that there was no way a signal could travel between the particles at the speed of light. The results were clear. Einstein was wrong. The particles were matching in ways that hidden variables couldn't explain. The spooky action was real. Since then, we have closed every possible loophole. We've done experiments where we use the light from ancient stars on opposite sides of the sky to decide how to measure the particles, ensuring that no human bias or local interference could fake the results. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their work on entanglement. They proved that our universe is fundamentally non-local. Things are connected even when they are apart. We are living in a world of ghosts, and we finally have the proof. You might be wondering, okay, this is cool for scientists in labs, but why does it matter to me? Well, it matters because this spooky action is the engine behind the next industrial revolution. The first big application is quantum computing. A normal computer uses bits, little switches that are either 0 or 1. But a quantum computer uses qubits, which are made of entangled particles in superposition. Because a qubit can be a 0, a 1, or both at the same time, it can process vast amounts of data simultaneously. An entangled group of just a few hundred qubits could, in theory, perform more calculations in a second than there are atoms in the known universe. This would allow us to design new medicines, solve climate change, and break any password on Earth in seconds. Then there's quantum cryptography. Because the act of observing an entangled particle changes it, you can create a communication line that is literally unhackable. If a spy tries to listen in on a quantum message, they will disturb the entanglement, and the sender and receiver will know instantly. We are already building quantum internets that use this technology to protect bank records and government secrets. And believe it or not, we are already doing quantum teleportation. No, we aren't beaming people like in Star Trek yet, but we are teleporting information. By using entanglement, scientists have been able to transfer the exact state of one particle to another one miles away without the information ever traveling through the space in between. It disappears from one place and reappears in another. Perhaps the most mind-blowing thing is that these ghosts might be inside you right now. Some scientists believe that birds use quantum entanglement in their eyes to see the Earth's magnetic field, allowing them to navigate across oceans during migration. There is even a wild theory that our own brains might use quantum effects to create consciousness. We aren't just living in a quantum universe, we might be quantum machines ourselves. But let's think even bigger. If entanglement can link two particles, could it be linking the entire universe? Some of the most cutting-edge theories in physics today suggest that space and time themselves aren't the base of reality. Instead, they might be emergent properties of entanglement. There is a famous equation in physics, ER=EPR. It sounds complicated, but it's actually a beautiful idea. It suggests that a wormhole, ER, is actually the same thing as an entangled pair of particles, EPR. In other words, entanglement might be a tiny, microscopic bridge, a wormhole connecting 2 points in space. If you have enough of these connections, they weave together to create the fabric of the universe. Without these quantum ghosts, the universe might just fall apart into a pile of disconnected dots. This leads us to the holographic universe theory. This is the idea that our 3D world is actually just a projection of quantum information stored on a 2D surface at the edge of the universe. It's like how a 2D credit card has a 3D hologram on it. If this is true, then everything you see, your house, the stars, the person you love, is just a ghostly projection of quantum data. Even black holes, the scariest things in the universe, are teaching us about entanglement. Scientists like Stephen Hawking struggled with the information paradox, the idea that information might be destroyed when it falls into a black hole. But by using entanglement, modern physicists are finding that the information might actually be preserved in the glow of the black hole, linked to the inside via these spooky connections. Entanglement is the key that is finally unlocking the doors that have been locked for a century. As we look toward the future, the quantum revolution is only just beginning. We are moving from a world where we just observe these ghosts to a world where we are starting to control them. We are building sensors that can see through walls using entangled light, clocks that are so accurate they won't lose a second in billions of years, and perhaps one day a way to communicate across the stars without any delay. But beyond the technology, there is a deeper, more philosophical lesson here. Quantum ghosts tell us that the universe is far more interconnected than we ever dreamed. We like to think of ourselves as separate individuals, floating on a rock in a cold, empty void. But quantum mechanics says that's an illusion. At the most fundamental level, everything is linked. Everything is part of the same grand, spooky dance. The spooky action that Einstein hated is actually the very thing that makes our existence possible. The universe isn't a machine. It's a mystery. It's a place where the impossible happens every day in the space between atoms. So, the next time you look up at the night sky, remember that those distant stars aren't just faraway balls of gas. They might be connected to you right now by invisible, ghostly threads that we are only just beginning to understand. We are the universe trying to understand itself, and the ghosts are finally starting to speak. If you want to see how this spooky action is being used to build the first ever time crystal, check out our next video.